In this video, I will be demonstrating the new updates to the fullrmc saas interface with some additional features, especially the structure tab here that would allow you to create a crystal system and work with it, because fullrmc, starting from version 5.0, it's crystal aware, and there is a lot of functionalities that will help you do crystalline structures very easily. And also on top of that, I will be showing the new viewer, which will help you not simply visualize and draw beautiful structure pictures for publications, but it will enable you to do better simulations, and it will help you set up your system as well. And I will go through examples and details to show you how to do this. So the first thing that you might have noticed is the interface is a bit simpler with new icons and stuff like that. I'm not going to go into the details. That's where you log in, you log out, you sign up, and this is where you have your settings. Let me show you here one additional feature in the settings, which is the preferences. And if you are an admin, this is how you can access the preferences, and you can set up the user's maximum idle time, beyond which the user will be logged out automatically, and the machine maximum idle time as well, beyond which if there's no user logged in on the machine would turn itself automatically to save you money when you're running on AWS or Azure, for example. So here, if you go to the engine tab, you can always create your engine or build it from a previously downloaded snapshot. You can add and create an engine that is meant for tutorial purposes. We will be doing another video about this at some point, but now let's skip it. There's nothing here more that you need to know about. In the structure section, and this is where it gets very important. So let me first create an engine, because it didn't allow me to go there because I haven't selected an engine. I'll create an engine, I'll call it Graphite, and create. Then now I will select Graphite, and I want to go to the structure. So this is a new tab that is added to fullrmc that exposes the old way of setting a structure, which is reading a PDB file, and that's always valid, and this is the normal input for fullrmc. But the added section here is using crystalline structure, which is you can load a CIF file, but we did it a little bit differently because not all CIF files are alike. You need to provide the crystallographic parameters for the unit cell, the symmetry operations, and the atoms, and you specify the size of the simple cell you want to create, and then you create the crystal and set as PDB. Let me give you an example of that. So here I have the CIF file. Let me bring it to the screen. So this is the CIF file I will be working with. Normally you can read a CIF file, but we did it in a safer way. So you need to provide A, B, C, alpha, beta, gamma, and they are here. 2.49 for AB and C 4.14. And here 4.14. I'll close this. And you have alpha, beta, gamma 9090 120, can be simpler. Then you need the symmetry operations. These are the symmetry operations, so you need to provide it as a list of strings. So let me show you how to do this. I'll do this now. I'll create this as strings. Oops. And then I'll do this, and I'll do this, and I will find now every new line, I will replace it with space and comma, just for beautification, replace all. So this is my symmetry operations. Now I need to create the atoms. And here the atoms in the CIF file are simply 2 carbon atoms at these coordinates. So let me do this. So you need to provide a list of tuples where each element of the tuple is the element itself, where each item of the tuple is the element itself with the 3 coordinates in the box, in the unit cell, and the occupancy if it is not 1. So here, the first element is carbon. Everything is case sensitive. So here I'm providing it as lowercase carbon, which is different than uppercase carbon, not from an element point of view, but from fullrmc's point of view. So there's no big difference, just so you are aware of it. So here the occupancy is 1, but I'm not gonna give it, there's no need. And then the second element is also carbon, so 0.33, and the last one is this. And be careful, that's not gonna work because I need to put commas here. Comma. So I'm sure you understand what is it now. So this is the unit cell parameters, the symmetry operations to create the atoms, and those are the atoms. And I will be creating a crystal, a supercell of 10, 10, 10. So what would happen here, fullrmc will parse those parameters, will create the unit cell, will generate the supercell, and it is done now. And this is the structure. And it will automatically compute the basis vectors for you. You cannot change the density here because it's set by the number of atoms and the basis vectors, or the lattice parameters that you see here in front of you. And these now are the lattice parameters for the supercell, not for the unit cell. So since it's 10, 10, 10, so you know it, you divide by 10, A, B, C, alpha, beta, gamma are always going to be the same. One thing you might have noticed here that I have 12,000 atoms that are generated, and I have 1,000 molecules, because fullrmc does that automatically for you when you create a crystal. And what happens is that each unit cell in this supercell will be created as a separate molecule, just for the simplicity of it. So you can create groups as unit cells, and you can perform moves upon those unit cells. For example, you want to simulate the unit cells orientation, because you know that you have different orientations of the unit cells, so you can do that easily. And each time you create a crystal, the residue is CRY for crystal. Here I have one element, carbon, so I see it here, 12,000 of it, and I have all of those carbon atoms by name. So frames is the same, I'm not gonna worry about it. A little bit different in the interface. So you used to be able to set the PDB from the frames. Now it's all moved to structure. There's nothing that you need to worry about. Now let's go to the viewer. And this is where it gets very interesting. And very interesting because this viewer is powered by 3D but we created our own version of it. And you can visualize very beautiful structures that takes into considerations the frames. If you have biological molecules, macromolecules, you can show and remove the hydrogen. You can make it dynamic upon selecting the frames, and we will demonstrate that. You would add multiple layers, keeping in mind that the layers are drawn in order. So you can one layer might update the parameters of the previous one. This is not a problem, but you just need to be aware of it to understand what's happening. So I'll remove this layer now. You can also visualize the boundary conditions. Now these are the boundary conditions. I can hide it, I can plot it, I can make it as dashed or not. I can improve the thickness, change the color. Let me come back here because we will use that later. 0.5. And one very important feature that you would be very interested to see, and I will demo it later, is because we are working here in boundary conditions that are periodic, and I will show you what periodic means here visually. Just to define it, periodic boundary conditions is a mathematical way to let fullrmc replicate this this box here or this model infinitely in the space, indefinitely in the space. So what that means is all atoms in the box are mirrored indefinitely in X, Y, and Z space. So you should imagine that there is a box similar to this, exactly similar to this, with the same atom position, just translated in X, Y, and Z. So you can always fold atoms into the box to make everything fit into the box, or not. You let it work that way. But now everything is going to be in the box by construction. Different systems, if you provide the PDB file by yourself, it's not going to be the case, and I'll be more than happy to answer all your question about this, but I'm not going to stop here now. And you also can build contiguous molecules. So let me demonstrate this here. So nothing happened because everything is contiguous now, but maybe we will show it when I demo the molecular systems. For Canvas, you can change the background color, the perspective. Let me do this. Okay, very ugly. And this is a perspective. And you can show and hide the Cartesian X, Y, and Z axes. You can change all of that. So maybe that's very ugly, but you can change it. What else? You will be able to reload the frame at any time, and this would be very useful when the engine is running, and I will also show it. You can reset the view to the original, and you can always export a snapshot. So now what I want to do is I want to hide the axes, and I will create this layer, and I will show you whatever you have here. So in every layer, you can select the atoms that you want to plot in that layer. So here you can do the selections by groups and by atoms. So you do two types of filters. We will talk about this just in a few seconds. And then you can hide and not hide. And you would choose how you want to draw the layer. So here, for example, I will do cross. So all atoms are crosses. You can specify the parameters here and the color scheme. And very importantly, you can, from the selection of the layer, the atoms that are selected, you can add this selection as a single group to the engine. So you can perform different types of movements on this group of atom, or you can create the selection as many groups as the atoms in the selection and add those or set those to the engine. So let me add another layer and you will understand what I'm talking about. So now if I zoom in, you have the previous layer in cross and the new layer in spheres. So the selection I want to do here is, let me say X, not X here. I cannot do this because this is for groups. I'll say X smaller than 10 angstroms, and then I'll apply. Okay, I'll say X smaller than one angstrom, and then I will apply. And see, I have a full layer here. Let me do it in Y or in Z. All right, this is what I want. See that? Let me change the color of it, make it spheres, which is the same, but I'll make it smaller here. And let me choose the color by name so I can, okay. So imagine now I want to, let me do this, smaller than 1, smaller than 10, Z 11. Let me see what I can get here. All right, I got this plane here. Let me think about it, about what I want to do. And let me do this here and whatever, Y smaller than 5. All right, let's consider this. I'm not gonna bother much now. Let's think that I want to move this plane in Z direction and create stacking faults. So you need to create a group that contains those atoms and specify the move for that group, the move generator. This is a very simple way now to see the group that you are creating. Then I'll come here and I can set the name or leave it as is. I'll set the name as my group. I want to create a group of all of these atoms in one group. So I won't check group per atom, and then I'll add this to the engine. And then he says, added all of the 150 atoms that you see here, and number of groups in the system now from 12,000 to 12,001. So let me open this in a new tab. Those are all the groups I have, and this is a newly added group. All right. So now I created a group from the visualization, and this is the group. And let me demo that to you. So let me hide this, and now I'll add this. And now I want to select by group. So I can say index equal or bigger than 12,000. Apply. No atoms found. Oh, bigger or equal, because it is 12,000, I guess. This is it. All right. Groups index start by 0. So this is the group I just created in layer 1. I'm able to even select it here. So equal, equal, I'm able to even select it. So you see how important that is. You see why this is very helpful. It's not just a visualizer, it's a mean for you to set up the engine the way you want. Now let me go to group generator. I'll come here, I'll select the group I just created, and I can give it a translation along axis. And this axis will be along 1 and 0. So I'll be translating in X and Y. Well, let me keep it 0 here. And this direction is true, false, or none, means translate towards the positive direction of this axis, the negative or randomly positive and negative. I'll keep it this way, and then I'll set this like that. And now when I run the engine, this group of atom, which is here, will be only moving and shifting in the Z direction. And that's how you start simulating, for example, stacking faults. So there is a lot of things you can do from this interface. And you need to understand that all the power of fullrmc is from the simplicity that you as a user can select atoms, group those atoms in bodies that we call group, and then let the atoms move in the way you want and you think they should, in order to bring the system or bring the structure to the hypothesis that you are trying to validate. And this is a visual way of doing it that help everyone do that in a very simple way. So enough with this now. Let me go here to engine, and I want to show you a molecular system this time, and I'll go to viewer as well. So this is a box of tetrahydrofuran. I can show hydrogen atoms or hide them. I'll keep it on. And here I want to show you the importance of the boundary conditions. So these are molecules. Let me say I don't want to fold atoms into the box. So let's see what's going to happen. And this is a little bit shocking, but now you would understand what boundary conditions are. Boundary conditions, as I said, is a mathematical trick to auto-mirror the structure of your simulation indefinitely in space. By definition, it's drawn starting from the origin, 0, 0, 0. So let me show you where 0, 0, 0 is. This is where 0, 0, 0 is. Those three vectors here. This is where 0, 0, 0 is. And it goes into the positive quadrant. Now the PDB structure I gave, it's centered around 0, 0, 0. But that's not a big deal, because this structure will be mirrored indefinitely in the space. So I can, fullrmc would take care of all of that for you. You don't have to worry about anything. Mathematically speaking, what's happening is the coordinates of the atoms are transformed via a matrix transformation or multiplication to bring everything into the box coordinate. If this doesn't make sense, do not worry about it. And that's how fullrmc propagates those coordinates indefinitely in the space. So visually, it's ugly. It's maybe a little bit ugly to do this, but I can tell fullrmc, you know what? Fold everything into the box. Give me the original structure. And now everything is brought into the box using the coordinate transformation. But what might happen here, because everything is now folded into the box, some molecules might be cut between the edges of the box, the facets and the edges. For example, there is no single atoms in my simulation. And here visually, I have the artifact of having a single atom. But actually what is happening here is, for example, this fragment of the molecule is continued by those atoms here. But when I fold everything into the box, nothing will go beyond the box facets. Technically speaking, the distance between this atom and this atom is not that much. It's actually way smaller. It's the wrapping from here to here. So maybe it's 2 angstroms. It's not the length of the box. So now to correct for this artifact, I would tell fullrmc to do its best to reconstruct the molecules, knowing that some might go beyond the box limits, but that's okay. And here you have it. These are the reconstructed molecules that we call contiguous objects. And technically, this is the exact distance between the atoms. If you tell it not to do so, it would be the atoms that you saw here before, now they are here below. So look at the atoms here now, and let me recheck this. And they will disappear and they will go up. Because this is the shortest distance. Reconstructing the molecules to be contiguous will let fullrmc visualize the system considering the shortest distance between atoms. And the shortest distance between this atom and this atom is that much. It's not from here to here like it was before. So what I want to do now, I would like to create a new frame. I will call it test. I will add this new frame and I will use this new frame. I will come back to visualizer and let me here show you some cool selections to start with. So first I'll come to groups. Groups are set as molecules. Perfect, that's all what I need. And then I'll say index equal 0. And here I'll have this molecule. So you see it's broken between here and here. Let me make it contiguous. All right. So let me also index in range 10. So I'll take the first 10 groups, which is 10 different molecules. And I'll also do the same trick here to show you how that works. All right. Now, what I want to do is, I'll keep it all here, and I want to show you some complex atoms selection, because you can select atoms using an expression, and the expression can contain different variables, and it's not limiting, it's very safe to use those variables. If you use other than those, everything would fail and it wouldn't allow you. So the variables are, you can select using the atoms index, residue, sequence number, segment, chain identifier, element name, XYZ. You can use mathematical functions like the sine function, cosine, exponential, tangent, square root, log, and you can use the operators equal, not equal, bigger or equal, so you know what I'm getting at. So let me now select a sphere. So the equation of the sphere would be square root of x square plus y square plus z square. I want it to be smaller than 10. Apply. So you see how it is? That's not a sphere. Actually, it is a sphere, but when I fold it into the box, that's what happened. Let me make it 12 here to make it a little bit bigger. And it is 4 sphere corners because I am folding everything into the box. Actually, this is a sphere. And the sphere is centered around 0. So let me do here x plus 5 square. See? Or x minus 5 square minus 10 square, and then it will be brought to the positive quadrant a little bit. So let me do that, keep it that way. All right. So I want to keep this like that. And what I want to do is to run this simulation using some move generators. And let me tell you what I want to do here. I want to create a selector, and the selector would be a directional order selector, and the center of this selector would be the geometric center 0, 0, 0. So it would be 0, 0, 0. I want to expand, and I want to adjust the move generator. I can do that. Create. Now what happens here is all the move generators for each and every group now is going to be adjusted when the engine starts running. I want to cancel all the constraints. I'm not going to make them, I don't want them to be used. So here it's the case for this. This constraint is not used, and this constraint is not used. That's perfect. So what I'm doing now, if you are following, let me see the selector. I'm using a selector that will expand my system, expand all the system. So when you are running an experiment in C2 and you're heating up, you're heating up your system, you would want to simulate that the system is expanding, unless it's ice and it shrinks. So to do so, I want to visualize that for you. I'll run this for a big number of steps. I'll run it. So there's no standard error, there is nothing, because I canceled all the constraints. And what I want to do here, I want to start updating the frames. So now what's happening is the selector is selecting the molecules from the outer layers to the smaller layers and performing expansion moves of that system. So look at it. See how it is expanding? And this is how you would do an simulation to expand your system in full RMC. And I'm able to show you how that works because I have a neat visualizer where I can track what's happening. Expand. So this is now a very wrong simulation what I'm doing, because I expanded the system, but technically everything is still within the box. So atoms are sitting on top of each other now. So you need to expand the box size and expand the molecules as well. But what I'm trying to show you here is how cool that is. So let me now contrast this with the original structure. See how we were? And now this is the new structure, the test. It's expanding. Let me come back to run, stop that, and come back here. So I don't like what happened here. What I want to do is I want to take the selected frame test and I want to reinitialize it to where it was before. So this way I would be resetting all the damage I've done. All right. Now what I want to do is to select, I want to first set groups as molecules. I want to take this group, just for the fun of it. I want to clear all groups, and then set this group alone. Set. Now I have only one group in my system. So I will take that, and I will make it crosses. All right, and I will give it one color. Atom pick. Okay, probably that's okay. Color pick. I'll make it that way. And then I'll create another layer, and this time it would be index equal 0. Apply. This is where the molecule is. You know what? I will hide this because that's too much. And I want to draw the axis. And what I want to do now is to bring this molecule, only this molecule, towards the origin. And let me show you how that would happen. So now I have one group. I will have this move generator, and I will say translate towards axis, towards center generator. So I will make a translation of 0.01 angstrom per step, a maximum towards the center of using an angle of 30 degrees. This is a divergent angle, so you need to imagine a cone going from the center towards wherever this atom is, and the angle of this cone of 30 degrees. So let me make it 5 here, so to make it smaller. So the same way, you can select whether you want to go towards the center, away from the center, or in both directions. First, let me go towards the center, and I want to make this smaller because that would go super fast. And now I have this move generator to that group. I'll go to run. Also, I want to run it for a huge number of time. So this is where the molecule is. And okay, this is actually where the molecule is in real space without it being folded. And then I would run. So it's a little bit slow because the distance I chose is slow, but just for the purpose of showing you what's happening. And now the molecule is always going towards that center. So actually what we are doing is demonstrating how fullrmc works and how everything you set affects the way you are fitting the system. And this is very important because that's how you test your hypotheses. This is how you test whether you can bring two molecules together, how you can open a DNA, how you can create stacking faults in your system, how you shrink your system. That's how you do it. So now I will stop this. I will go back to generator. I'll select this and I'll translate towards center as well. And this time I will go by 0.1 and I will go away from the center in an angle of 30 degrees, whatever. I'll set it. I'll go to here and let me run it. So this is, let me start by updating this. This is where the molecule is now, exactly at the center. Now I would update it. I would run that for a huge number of steps. I will run and look. This will keep going away indefinitely. Keep going away, even beyond the box size. But that's okay. This is not a problem because we are in boundary conditions. And remember, if I fold everything into the box, this is the actual distance from the center now, and you will see it. Everything will go, it will go back to the other side of the box. It will travel through the box and come back from the other side. See how the atoms are split here? Because it's traveling from one side to the other. And what's happening is it's getting split, but this is a visual artifact. It's split across the facets of the box. Technically speaking, where the molecule is actually the real coordinates, not the box coordinates. Look how far the molecule is now. That's where it is. Super far from the box. But even though it's super far from the box, this is just an image of the molecule. The actual position is in the box. See how far it is? Now, if I want to draw it within the box conditions, this is where the molecule is. It's always going away from the center, but what happens is the more it goes away, it finds itself going out of a facet and coming back from the other side. That's what's happening. That's very important. So if you expand your system in boundary conditions, when you have periodic boundary conditions, and you expand your system without changing the boundary conditions dimension, you wouldn't be expanding the system. You wouldn't be doing anything, because you wouldn't be actually changing the density of the system. You wouldn't be lowering the density of the system, because the boundary conditions decide this. So that's a great demo of the visualizer and why now you need to focus on the visualizer to set up your system. As we said, you can set how, for example, layers of the crystalline structure you have needs to move to create stacking folds, to do stuff like that. So now let me visualize something super cool. Let me go to atomic nickel titanium and go to visualizer. This is the initial structure. Let me plot it differently. Spheres. Make it smaller. All right. This is frame 0, the original structure. This is frame 1. That's what happened. And this is frame swap after swapping some atoms. So the way that would work is as follows. I will create 2 layers. Well, you know what? I don't need 2 layers. Let me kill this layer. In this layer, I would like to select everything that is up beyond 10 angstroms. All right, this is it. What am I doing here? Let me remember what I should do. And element equal titanium. Apply. I'm selecting only titanium. And in another layer, I want to select element equal nickel. And this selection, I will make it as crosses. Oh, well, you know what? This is cool. Balls and sticks was cool. And I'll make this a little bit transparent. Sticks. Let me do sticks. And I'll make it transparent. A little bit transparent. All right. Now this is frame 0. This is frame 1. This is frame 0. That's frame 1. And the reason why you don't see anything in frame 0 because the distances are far away. So let me do this now. That's ridiculous. Spheres. Let me make it smaller. Okay, that's frame 0. Can I do lines? And if I go frame 1, that's ugly. Cross. Okay, that would be okay. Let me change this color because that's ugly. Yeah, that's neat. Now, that's what happens when I move the atoms. And when I swap, after swapping, you see how the nickels and the titaniums are scattered around now because I did some swapping. So in this system, some swapping was happening, and I'll demo that to you. So what happens here is that the selection didn't get updated, and this is done purposefully, just so we can visualize the difference between frames. If you don't want this to happen, if you want the selection to be updated all the time, you just need to click that, and the selection will always be auto-updated. All right, so let me uncheck this and show you this back again. So these are the atoms that are selected by index using these filters, the X here, especially the X. Now, when I change the swap, I won't be updating the selection. The indexes will remain the same. And notice what happened. Atoms that were in this slab here, they are swapped with nickels that are outside of that slab.